We'll now look at the second video from section 4.6. This is about a solution strategy to related rate problems. Now, we want to begin by establishing a difference between calculus and algebra. The difference being that calculus is always able to deal with change. And in this case, we're really focusing on change over time. The example from the previous video where we had a sphere and a cone really illustrated that it's not too tough to move from a formula relating static variables, so this would be like algebra and geometry, to a formula that relates their rates of change. This is the calculus. All it really involved us doing was differentiating with respect to time and working the calculus like an implicit differentiation problem. So what this will do for us then is introduce an important category of new problems called related rates problem. So that's where we're going to be heading next. Those constitute one of the most important applications of calculus. And in the next two slides, we're going to look at a strategy for solving those problems, similar to a strategy of max-min problems that we saw in previous days. So here we go. This strategy, it's going to look a lot like what we did in example one. First, understand the problem, read it, make sure you know what type of quantities are going to be variables, what type of quantities are going to be constant, and what kind of quantities you're trying to find. What do you seek to know? Next, number two, you want to develop a mathematical problem, a mathematical model of the problem. My favorite part, draw a picture. That's what I do first. Draw a picture. You saw me draw the sphere. You saw me draw the cone. I'm going to draw some more pictures in this video, but make sure you understand exactly what's going on. Most of the time, that means getting yourself either a mental or physical model. Number three, write an equation that relates the variables whose rates of change you seek to find. This is where we start out with that relationship equation. In the last example of volume, we said volume of a sphere is 4/3 pi r cubed. We said volume of a cone is 1/3 pi r squared h. It's where you take a look at your model and come up with a way that all of those variables are related. After you do that, you want to differentiate both sides with respect to t. So this is the step where we go ddt both sides. Be sure to follow all your differentiation rules. You're going to work with the chain rule because you're going to be doing some implicit differentiation. And then number five, substitute the values that we know. This is what we haven't seen so far. In the following problems, we're going to be given some quantities. Some of them will be moments in time of measurements. Some of them will be rates of change. But at a particular moment when we have our example of movement, of motion, we're going to freeze the picture. We're going to say, okay, at one time, now tell me about a rate of change, or now tell me about a variable. And then finally interpret that solution. In other words, label your answer. What have you found? If you found a rate, then you need to label it like a rate. Is it feet per second? Is it cubic inches per minute? What have you found? So that takes us to example two. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radian per minute. How fast is the balloon rising at that moment? So first, let's understand this question. We're given some information about a hot air balloon and a rangefinder that are 500 feet from one another. That's an important piece of information. We're talking about an angle of elevation of the rangefinder, and also that angle is increasing. So that tells me I need to have an angle as one of my variables, and I need to consider the rate at which the angle is changing. And then finally, we're asked, how fast is the balloon rising? So that's going to be another rate at which the balloon is moving upwards. So I think the next thing I'm going to do is get a little bit of a model. So here's going to be my grass. I'm going to draw the hot air balloon. Let's get another color here. So there's the basket of my balloon, and there's the strings holding the balloon up. And then that's rising. I'm going to draw a little arrow showing that's going straight up. And then 500 feet away is a rangefinder. I'm just going to note that by a dot. This is going to be 500 from the liftoff point. And then that rangefinder is tracking the hot air balloon. and that angle is changing as the hot air balloon rises. Now, the only thing I haven't really labeled on here that I probably should is something to do with the height of the balloon, because we want to know how fast it's rising. So let's just call that h, the height of the balloon. So there's our model. And the next step is to write an equation that relates all of these pieces. So here's what I have. I've got an angle. I have that angle inside of a right triangle. The side opposite to that angle is h, and the side adjacent to that angle is 500. So if I'm looking at an angle, an opposite, and an adjacent, to me, that says I have a tangent statement I can make. That the tangent of theta, that's that angle, is equal to h over 500. So there's my relationship equation. That means I get to move on to the next step, which is to differentiate with respect to t. So let's take ddt of the left, let's take ddt of the right, and let's move on. So first, the derivative of tangent is secant squared. So secant squared theta. And then implicitly, we found the derivative of a theta. So now we multiply by d theta dt. On the right, h over 500, that's the same as saying 1/500th h. So let's do that. 1/500th then times dh dt, since we differentiated h. So here we are. There's the result of that step of taking the derivative with respect to t. Now we get to plug in what we know. So here's what we were told, that at the moment the rangefinder's elevation angle is pi over 4. So we freeze time. The angle in question is pi over 4. The angle is increasing at a rate of 0.14. So that's a rate, and in particular, it's d theta dt. So this gets replaced by 0.14. And it's positive because we were told it was increasing. If we were told it was decreasing, we'd make that a negative 0.14. On the other side, there's a variable still, dh dt, and that's what we're trying to find. I'm going to leave a question mark there to indicate that, because we were asked how fast is the balloon rising. Okay, so let's go from here. So we've got secant squared of pi over 4, secant squared of pi over 4, and then times a 0.14, and then that's equal to 1/500th dh dt. And then we need to continue on with the work. Well, secant of pi over 4 is the reciprocal of cosine. So cosine of pi over 4 is root 2 over 2. So the reciprocal is 2 over root 2. And that's squared times a 0.14 equals 1/500 dh dt. So then if we take 2 over root 2 and square it, we get 4 over 2. And then we take 4 over 2, and that's just 2. So that gives us 2 times 0.14. So that becomes, what? 0.28 equals 1/500th dh dt. And then we need to multiply both sides by 500 to solve for dh dt. And this becomes 140. 140 is dh dt. So we found the variable in question. The last thing is interpret that answer. It's a rate. It's the change in height with respect to time. So it's not just 140 as an answer, it's 140 units. And those units in this case are going to be, well, we're measuring things in feet. So 140 feet per minute is the other way we're measuring. So 140 feet per minute is the rate of change in the balloon rising. This question is from the textbook. We'll leave that for class time, and let's go to another example. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now heading straight east. So I'm going to pause right there for a second and start my model. A police cruiser approaching a right-angled intersection from the north. So he's going this way. A right-angled intersection. He's chasing a car that's turned the corner and it's now moving east. So that would be this way. Here's a right angle. So here's my police car, And over here is another car. I'm just going to call it C for car. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So it looks like we're measuring this distance as well. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, we need to label some things here. And I think just to keep it easy, on the horizontal, I'll call that X. On the vertical, I'll call that Y. And then on the hypotenuse of this right triangle, that's the distance between the police cruiser and the car, let's call that D for distance. Okay, so how are those related? Well, this is a right triangle. They're related by the Pythagorean theorem. So let's do that. We know that x squared plus y squared equals d squared in this example. Now, x is changing with time, y is changing with time, and the distance between those cars are also changing with time. So I think now we have to take a look at finding the derivative with respect to time of both sides. So there we are. Now, as we move forward, let's go ahead and differentiate. The derivative of x squared is 2x, and then implicitly times dx dt. Plus, the derivative of y squared is 2y, and then implicitly times dy dt. And finally, on the right, we have 2d dd dt. That's a lot to say in one mouthful. 2d dd dt, 4 d's in a row. Okay, next. Now, we've done the derivative part. Calculus is over. Now we start plugging in the things that we know. When the cruiser is 0.6 miles north, so at this moment in time, the cruiser is 0.6 miles north of the intersection. The car is 0.8. So there we have those. That means I get to replace the x with a 0.8. I get to replace the y with a 0.6. The police determined with a radar that the distance between them and the car is increasing at 20 miles per hour. So that's the rate of change of the distance. That's 20. If the cruiser is moving at 60 miles an hour, so that's the rate of change in the police cruiser, which in this case, that's reflected by dy dt. The cruiser is moving at 60 miles an hour. What is the speed of the car? So the speed of the car, that's the change in x. That's dx dt, what I'm trying to find. There's still one variable left. That's the d over here on the right side, 2d dt. But since these variables or functions were related by the Pythagorean theorem, I can kind of solve for d. If I say that distance squared is equal to 0.6 squared plus 0.8 squared, I can solve that. And I'll find out there, this is a 3, 4, 5 triangle, so the distance is 1, and I can replace that d in that equation with a 1. So here's what we have next. 2 times 0.8 dx dt plus 2 times 0.6 times 60 equals 2 times 1 times 20. We're solving for dx dt, so that gives us 2 times 0.8, that's 1.6 dx dt, plus 2 times 0.6 times 60, so that'll be 36 times 2, that'll be what, 72, correct me if I'm wrong, and then that'll be equal to 40. I think maybe I am wrong on that one, 272. All right, and so finally you want to finish up your algebra there, and we should end up, oh, you know what? I made a mistake. Let's go back here, guys. This shouldn't be 60 miles per hour. That should be negative 60 miles per hour. Take a look. Variable y is getting smaller. It's decreasing. That's why this looked a little bit strange. So this is not plus 72, it's minus 72. Now if we finish off that algebra, we should end up with dx dt is 70. That's the rate of change in the car, and that's going to be in miles per hour. The next example is from your textbook. We'll do it in class. And finally, that takes us to example 4. We're going to work that one in class too. Stay tuned for more videos from both the book exercises and from the, let's see, the AP Calc problem book assignment that we got as well. Thanks for tuning in.